Write down diffraction. What is diffraction? Understand this way. This was main source S, and then we cut open two slits, S1 and S2. Here lies your screen. Now, from ray optics, you know law of rectilinear propagation, that light always travels in what? Straight line. So fundamentally, light coming from S through S1 should reach this point on the screen. Similarly, light coming from S through S2 should reach this point on the screen. But if light moves like this, then you cannot have any interference. This wave cannot interfere with this light wave. They are arriving at two different positions on the screen. So in fact, in reality, what happens when light arrives, it bends, light bends coming from these things. Now, these waves coming from S1 and S2, they interfere with each other. So instead of having a rectilinear propagation, interference tells us that light is bending at this position of S1 and S2. This bending is called what? Diffraction. Again, suppose you have a very sharp blade. This is a side view of the blade, a razor blade, and I'm showing you the side view of that that razor blade. You have a screen in front of you. If light arrives from this side, then in normal condition, what would you expect? These are parallel rays, and therefore they can only reach this, and this portion will be the shadow part. This thing is going to cast a shadow on the screen. That's the shadow part. That's what you will expect. But what is observed? That when light arrives at this sharp edge, we find that there are certain positions over here which are not completely dark. Shadow means what? No light at all. But in reality, we find that there are fringes present. There are dark and bright spots present. That means instead of moving in the straight line path according to rectilinear propagation, these light rays, they bend at this. That means at the corner, at a very sharp corner, this bending takes place. Why the bending takes place, we'll understand everything once we discuss this diffraction. What the bending is basically, this is nothing but Huygens principle. So this bending process is called what? Diffraction. Draw these figures for your understanding. This is a razor blade, something which is very sharp. Draw the figure first. write down a statement. Bending of light around sharp edges, bending of light around sharp edges is called diffraction. Bending of light around sharp edges is called diffraction. Now, what basically diffraction is and how come this bending takes place? Let's understand this with the help of Huygens principle. Look here. This is one of the slits in YDSE, S1 or S2. If you zoom in, you will find this much spacing. And a parallel wavefront is reaching this slit. This is your YDSE, source, S1, S2, and the screen. Let's say this source is at very large distance, and for simplicity also assume that source is right here, just in front of S1. Instead of this position, if I take S over here, it will be easier for us to understand the concept of diffraction. So what we are doing is something like this. This is source, just in front of S1. And this distance is very large. So all the waves coming from S, you know that it will be giving us a spherical wavefront. These are not circular arcs, these are what? Complete spherical wavefronts, and they are reaching S1. Size of S1 is what? Very small, and therefore when these wavefronts reach this place, they will just look like what? Parallel wavefronts. So this opening, small opening, is this much. And when a particular wavefront reaches, we are interested only in this portion. Look at this line if you can see. So this line is what? Just a plane part. That's your plane wavefront. So all these are plane wavefronts. And if these are wavefronts, you know that light is traveling in this direction. This gives you direction of speed of light. Wave is traveling in this direction. These are your parallel wavefront. This is the opening. That's the actual setup. Spherical wavefronts. Once they reach, I'm interested in this part. Now, once a given wavefront reaches this opening, Huygens tells us that every part of this wavefront becomes what? A secondary source. So this plane wavefront has reached this opening, and then every point is now what? A secondary source. The way we used to define that if everybody on this wavefront says A, small 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 a. So when this small a reaches this position, all these secondary sources, they are also saying what? A. They all are in same phase. So remember, these are what? Secondary sources. Then here lies the screen. That's the screen. Now, what is going to happen? These secondary sources, all these point sources, they will emit what? Spherical wavefronts. So all these spherical wavefronts are going to reach a given point on the screen. I have shown you direction of propagation. From all these dots, this is what is happening. These dots, they are emitting what? Spherical wavefronts. These dots, they are emitting what? Spherical wavefronts. So at any point on the screen, if you go, you will find that, let's say this is some point on the screen. So what you are saying that light is coming from this, following this red path, from this, following this red path. I have shown you with these arrows, things shown in red. They all are emitting what? Spherical wavefronts. So these spherical wavefronts, when they arrive at any given point, will show them now in this form, which immediately explains what happens in diffraction. Why do you see light reaching other points? Normally you would expect what? You have an opening. If you have an opening, then light should be present only in front of the opening. Only this portion of the screen, this portion of the screen should get the light. But Huygens tells us that these secondary sources, they are emitting their spherical wavefronts, and therefore light is reaching everywhere. Now, when light reaches on these points, you can see that positions of these secondary sources with respect to this point is different. That means light has to travel different path lengths. If light travels different path lengths, then all these waves will interfere, and depending on the phase difference, you will see constructive or destructive interference. Listen again. In diffraction, we are talking about interference. What is interference? When two waves or their electric fields interfere with each other. So this source, secondary source S1, sends some electric field. Next one, this also sends some electric field. Third one, this also sends some electric field. All these electric fields, when you superimpose these electric fields, depending on the final vector sum, if it is maximum, you're going to see bright spot. If they all cancel out each other, you will see a completely dark spot. And that's the reason we see bright and dark fringes on the screen away from the portion on the screen which is just in front of the slit opening. How does this mathematically explain? We'll see that. But first draw this much. Draw this figure. It's a rough figure for you. Draw this rough figure. Draw this one also. These are these small secondary sources. And then we'll see the mathematical part. Note down this much. This is the central line. Now, how do we find positions of those maximas and minimas, bright fringes and dark fringes? Let's divide all these secondary sources in two partitions, upper portion and a lower portion. Just have patience and everything will be clear. So let's say there are 3 in the upper portion and 3 in the lower portion. There are many, infinite, in fact, infinite. But for your understanding, let's say there are 3 secondary sources in the upper region and 3 secondary sources in the lower region. If at a given point waves coming from first secondary source of the upper region and first secondary source of the lower region, first of upper and lower, if these two interfere at P such that path difference between these two rays is lambda by 2, then at P destructive interference is going to take place. What is the path difference? Lambda by 2. These are coherent sources, coherent secondary sources. A. Everybody is saying A. A. This A and this A, but have a path difference of lambda by 2 because of these geometrical lengths, and therefore a destructive interference takes place over here. What is that position? We'll define that position with the help of this red line. This angle is theta. I hope you can see this. This is theta. Now, for that point, we need to find path difference between these two waves. How do we do that? Suppose this slit size, let's say is A, the opening. Let's call it what? A. If this opening is A, then distance between any two, the first and the first, will be A by 2. There are two partitions. First distance between these two will be what? A by 2, which is equivalent to small d of YDSE. In YDSE we had what? S1 and S2. For the time being, consider this as S1 and this as S2. So what was the distance between S1 and S2? Small d, which in this case is what? A by 2. If this is A by 2, then this lambda by 2, which is the path difference, is basically what? D sine theta. In YDSC derivation, I hope you remember that when light from S1 and from S2 reaches a point on the screen, we used to drop a perpendicular. This much was d sine theta. This was small d. This was angular position theta. This is something which we have already done in YDSC. Same thing over here. For this secondary source and for this secondary source, when they interfere at point P, whose angular position with respect to slit, remember it's a very small slit, with respect to slit, angular position is what? Theta. Therefore, path difference at this point will be what? D sine theta, which is equal to what? Lambda by 2, and therefore both ways are going to cancel each other. This d then becomes what? A by 2 sine theta lambda by 2, which is A sine theta equals to lambda. Now, once you say that first and first of these two halves cancel each other, the electric fields cancel out each other, we can say that secondary source of the upper region will interfere with the secondary source of the lower region, and by symmetry we can say that they will also have a path difference of lambda by 2. This cancels this, and therefore we are saying that this will cancel this, third will cancel third, fourth will cancel fourth, fifth will cancel fifth. If you maintain d sine theta equals to lambda by 2, that means every secondary source in the upper region, its electric field is getting cancelled by the electric field of these secondary sources present in the lower region. No electric field survives at P. If no electric field survives, that means it is what? A completely dark spot. We have found first dark fringe and its angular position. What is theta 1? Theta 1 is this. This is your theta 1. This is your theta 1. This is your theta 1. First dark fringe, its angular position is given by sine theta 1 equals to lambda upon A. We are interested in the angular position. So this theta is what? Angular position with respect to slit of this point. The main thing is what? If first cancels first, then since slit size is very small, this S1, this opening S1 is the whole thing. And capital D, the screen distance, you know, is already very large, and therefore this approximation that whatever path difference is present between these two is also for second, is also for third, is also for fourth. With the help of YDSC and Huygens concept, we have defined angular position of dark fringe, first dark fringe on the screen. We'll write a few statements, but if you understand this part, this calculation work, then write down yours in the comment box and note down everything. Now write down the statement. Slit opening is divided into two segments, upper half and lower half, upper half and lower half. There are secondary sources present. There are coherent secondary sources present in both these halves, and light waves coming from these secondary sources interfere at point P. When angular position of P is theta first, first secondary source of the upper portion and first of the lower portion have a path difference of lambda by 2 at point P. That means their electric fields cancel each other. Now since slit size inside bracket A, since slit size A is very small and distance of screen is very large, we can say that same path difference of lambda by 2 is present between second of upper and second of lower, third of upper and third of lower, and so on, which means at point P no electric field is present. At point P no electric field is present, and therefore a complete dark fringe forms at P. A complete dark fringe forms at P. Angular positions of dark fringes. This is the first one. The next time what we did, we take some other angular position. We'll show it with the help of P only, but it is some other point P. Some other point, and we wish you can take it as a different point Q. Doesn't matter. Let's call it Q. Some different point. And this angular position is theta 2. This time what we did, we have divided the slit opening A in 4 equal segments. So these are the 4 equal segments which you see. First, second, third, fourth. And all these segments have their secondary sources. These are the 4 partitions, imaginary partitions. In the first case, we did 2 partitions, and now we are doing 4 partitions. So when you do 4 partitions, this first and this first secondary source of the first partition, first secondary source of the second partition, distance between these two will be what? A by 4. There are 4 partitions, and therefore this distance will now be what? A by 4. Light waves arriving at Q from these two therefore will have a path difference of d sine theta, small d sine theta, which is now A by 4 sine theta. Between this and this, now distance is what? A by 4, and therefore path difference will be A by 4 sine theta 2. And if this path difference is lambda by 2, then again this and this, the electric fields will cancel each other. So the electric fields cancel each other, we'll say that second and second, third and third, they will also cancel each other, and same thing is going to happen with third partition and fourth partition. First of third is going to cancel first of fourth, second of third is going to cancel second of fourth, which means again at this point Q, no electric field is present, and this place is completely dark. A destructive interference takes place because of what? Lambda by 2. And we have found next angular position, which is coming as what? Sine theta 2 equals to what? 2 lambda divided by A. This is the angular position of second dark fringe. Over here, we'll write it in this form: A sine theta 2 is 2 lambda. This gives us an interesting result. What is that? If I divide the whole thing, the whole slit A in 4 parts, then I get what? 2. Half of 4. In the first one, I had divided the whole thing in two parts. And what did I get? 1. Next time, we'll divide the whole thing in 6 equal parts. So if you divide the whole slit in 6 equal parts, first and second, they will cancel each other. Third and fourth, they will cancel each other. Fifth and sixth, they will cancel each other. So let's be fast. If you divide the whole thing in 6 partitions, this thing will remain what? A by 6. A by 6 and lambda by 2. Transfer 6. 6 upon 2 is what? 3. That means third dark fringe will be given by 3 lambda. 6 partitions, 6 by 2. That means nth dark fringe it will be what? A sine theta n equals to n lambda. So if we need angular position of nth dark fringe, write down n lambda. But now remember, some of you might think that when path difference was n lambda, we used to get what? Bright fringe. So this is not n lambda, this is basically lambda by 2. This 4, when you transfer it here, it becomes what? 4 by 2. So remember, we are again using the same thing. If path difference is what? Lambda by 2, you get what? Dark. That's what is happening. Every time path difference is what? Lambda by 2. But this transfer of 4, transfer of 6, transfer of 8 is giving us a look of n lambda type. This is the formula for dark fringe position. Dark fringe position. Note down this. Write down this. For nth dark fringe, 2n partitions. For second, how many partitions are there? 4. For nth dark fringe, 2n partitions are done. For nth dark fringe, 2n partitions are done. Phase difference, path difference between secondary sources of first and second partitions is lambda by 2. And same is for third and fourth, fifth and sixth, and finally between 2n minus 1th and 2nth. If there are 2n partitions, just before 2n is what? 2n minus 1. So if you make 16 partitions, 17th and if you make 16, then 15th and 16th. Which means for the corresponding point on the screen, no electric field will survive and it will be a completely dark spot. And it will be a completely dark spot. Let's talk about bright fringes. Angular position of bright fringes. Let's find out this. Say we have a point P, and this time what we did, we'll divide the slit size in 3 equal parts. First, second, third. There are secondary sources present. Between these first and first, path difference will be what? A by 3. 3 partitions, and therefore first and first A by 3. When light reaches this point, this angular position is theta first. If again path difference between these two, shown in black, is lambda by 2. What is path difference? Path difference is A by 3 sine theta, which gives us sine theta as 3 lambda by 2. But now understand what is happening. First secondary source of first partition, first secondary source of second partition, they have a path difference of what? Lambda by 2. And same is the case with second, third, fourth, fifth, sixth. As many secondary sources which are present in the first partition, that many are present in the second one. So, all the secondary sources of first, they are cancelled by the secondary sources of second, because they have a path difference of what? Lambda by 2. And because of this, destructive interference will take place. Destructive interference between these two waves, because they have a path difference of lambda by 2. Now, for this third partition, its secondary source, these secondary sources of third partition, they are free, and the electric fields will reach this point P. The electric fields will reach this point shown with the blue color. And these electric fields are not going to be cancelled, because there is no fourth partition. We did only 3 partitions. First and second, they cancel each other. Third is left out. That means what? All these electric fields, they survive at point P, and if they survive, that means electric field is present. Electric field is present, and therefore That spot is what? Bright. And will give you bright fringe. And first bright fringe, its angular position is coming what? 3 lambda by 2. Next time, we'll do what? How many partitions? 5. Let's save time. So when you make 5 partitions, first and second, the electric fields will cancel each other. Third and fourth, the electric fields will cancel each other. But fifth one, its electric fields will reach at P and are going to survive, giving us what? A bright fringe. So destructive interference is happening between, destructive interference takes place between first and second, third and fourth. But the last one, fifth one, it survives. That will give you what? If you are making 5 partitions, this will become what? A by 5. This will be lambda by 2 only. Transfer 5 here and you get A sine theta as what? 5 lambda by 2. This is your second bright fringe, its angular position. If you understand the way bright fringe forms, cancellation of 1 and 2, survival of third, then write down yes in the comment box and then we'll write a few statements and also give me formula for nth bright fringe. Look at the formula for nth dark fringe, nth bright fringe. It's a simple question. Nth bright A sine theta n. When this is 1, this is 3. What is that? 2n plus 1. And this is 2, this is 5. 2n plus 1. The formula is what? 2n plus 1 lambda by 2. This is the formula for nth bright fringe. Wrote down the formula and then 2-3 lines. Wrote down this formula first. Write down the statement. For bright fringes, slit is divided into odd number partitions. For bright fringes, slit is divided into odd number partitions. For first bright, we make 3 partitions. For first bright, we make 3 partitions. Secondary sources of first and second partition. Secondary sources of first and second partition. Maintain a path difference of lambda by 2. Thus cancelling out each other. But electric field from the secondary sources of third partition, but electric field from the secondary sources of third partition survives at point P on the screen, giving us a bright fringe, giving us first bright fringe. Next, we'll make 5 partitions. Next, we'll make 5 partitions. 1 and 2 will cancel each other. 3 and 4 will cancel each other. And 5th will produce second bright fringe. Light coming from 5th will give you a bright spot, which is your second bright fringe. For nth bright fringe, 2n plus 1 partitions are made. For nth bright fringe, 2n plus 1 partitions are made, in which 2n plus 1th partition, produces nth bright fringe. In the next class, we'll discuss difference between interference and diffraction. They are basically interfering with each other. So what is fundamentally different in diffraction and the interference part, and also the intensity pattern. Note down this much and then you can leave. Thank you very much.